Today we're going to be studying section 6.1, slope fields. The objective for today is you will define slope fields in relation to differential equations in order to create and match slope fields to their appropriate differential equation. So we need to understand what a slope field is, learn how to create it, and learn how to match it to its differential equation. Let's get started. First of all, what are slope fields? Yesterday we learned that differential equations give us the slope at any point of a function or relationship. Doesn't have to be a function. dy dx equals the slope of a tangent line. When we graph the slope of the tangent line to a function at various points, the result is going to be a slope field. So a slope field is a result of all of the slopes of tangent lines at several points, and those slopes come from the differential equation dy dx. Let's construct a slope field to better understand what I mean. We're going to start with a basic example. Construct a slope field for dy dx equal to cosine of x. So our differential equation dy dx is cosine of x. This is giving us the slope of the tangent line at various points. From yesterday, the solution to this should be very obvious, using the antiderivative, of course. But what we're going to do is we're not even going to bother with that. We're going to go ahead and simply use the idea that these are slopes of tangent lines to create our slope field. First of all, here's my set of axes, and instead of label these as 1, 2, and 3, we're going to use radians. So we're going to go ahead and label this pi halves. Now my tool is a little difficult to use, so you'll notice my writing's a little sloppy, but I think you'll be able to tell what it is. So 3 pi halves here, and of course negative pi halves, negative pi, oops, and negative 3 pi halves. We're going to go ahead and let this one equal 1, 2, and 3, negative 1, of course, negative 2, negative 3. And we're going to start picking values. I'm going to start with the easy one, the origin, 0, 0. Now if you notice, there is no y value in this differential equation. There is no y value. So that means that it's not going to have an impact on the direction of the slope. The only thing that's going to impact our slope is then going to be x. So letting x equal 0, we're going to go ahead and plug that into our differential equation, cosine. So cosine of 0 then becomes 1. So my dy dx, or my slope of my tangent line, is 1. So I'm going to go to my point x equals 0, and I'm going to go ahead and graph the tangent line. It's just going to be a mini tangent line. It's not going to be very long, of slope 1. So at the origin, I can think of going rise 1, run 1, or the equivalent, which is down 1, left 1. But either way, what I'm going to do is create a little tangent line that goes in that has slope 1, so it goes in the direction of the point 1, 1. Because I know that x is going to equal 0 at the point 0, 1, 0, 2, 0, 3, 0, negative 1, 0, negative 2, and 0, negative 3, I know that the slopes at those points are going to be identical to the one in the origin. Again, the y having no impact. So I'm going to go ahead and at the point 0, 1, my slope should also be 1. So I'm going to direct it one more time. I'm going to direct it rise 1, run 1. So I'm going to direct it towards 1, 2. You're going to notice that sometimes this is not perfect. You just do the best that you can to angle it in the direction, especially here where I can't quite see where the point is. I can, however, think of it as down 1, left 1. Okay, here we go. And essentially, all of these tangent lines here should have the same exact slope of 1. Picking x equal to pi halves next, you will see that cosine of pi halves, whoops, cosine of pi halves is going to equal 0. Now, x is equal to pi halves here on the x-axis, but it's also equal to pi halves at pi halves comma 1, pi halves comma 2. So all along this vertical line, x equals pi halves all the time. So my slope is going to be 0, which means it's a little horizontal line. Just like this. And this pattern is happening because there is no x value in the differential equation. So that means that x is the only thing that impacts our slope. So we get a bunch of slopes of 0. Okay, moving on to pi. At pi, the slope is -1 because cosine of pi, of course, is -1. So when I get to x equals pi, I need to, instead of going up 1, right 1, I need to go down 1, right 1. So my direction is with a negative slope. Of course, that's going to repeat all along the line x equals pi because, again, y does not have any impact on my slope. And you can see how I start building these slopes. So I'm going to ask you to press pause and go ahead and fill in the table and draw your slopes for 3 pi halves, negative pi halves, negative pi, and negative 3 pi halves. When you have completed it, go ahead and resume the video and compare your results to mine. Okay, here's the results of my table. These are all my slopes, and when I graph them, it looks like this. So this is a slope field. It's literally a field of little slopes, and it's constructed from the differential equation cosine of x. So this is really where we stop. Construct a slope field. This is it. We've done it. But what I'm going to do next is I'm going to trace and show you something kind of interesting. If you kind of follow these slopes and trace them, here we have a 0 slope, but you can see how it becomes negative. Then it becomes 0. One more time. Then it goes back up to positive, 0, negative, 0. And you get something very interesting. This is not the graph of cosine. Remember, cosine is actually supposed to be 1 at 0. Okay, but what this is the graph of, you got it, sine of x. Now, what you should notice that's interesting about this is from yesterday, the differential equation dy dx is solved by the antiderivative. So its solution is, the general solution that is sine of x plus c. Well, this happens to be sine of x plus 0. If we trace above, this one here follows 0 and goes back up. 0, and you can tell it's going to go back up. What you'll notice is that now this is really sine of x plus 1. Okay? I can also go below 0, negative, 0, positive, 0, negative, 0, and the result, of course, sine of x minus 1. So I'm going to go ahead and ask you guys to pause the video for a little bit, and in your notes, trace the 2 and the 3, and then the negative 2 and the negative 3, and compare your results to mine. Okay, so this is the result of me tracing it, and again, mine's a little bit messy because of the tool I'm using. But you can see how you're going to get sine of x plus 1 plus 2 plus 3 minus 1 minus 2 minus 3. Therefore, the result of this is the family of functions. This is called a family of functions that represents the solution to the differential equation cosine of x. So this slope field, when traced, gives the family of functions that solve the differential equation dy dx equals cosine of x. And of course you know that solution is sine of x plus c. Notice that we did not need the sine of x plus c to generate these curves. We did it by simply tracing the slopes that came from cosine. So this is going to be a really powerful thing to know. Yesterday, of course, we discussed how to solve a differential equation using the antiderivative. This is going to give you a picture of the solution without knowing what the solution is. Of course, the solution to this equation is easy, but in the future, there might be differential equations for which the solution is not so easy, but we still are able to generate a picture of what that would look like. And that's very powerful. Next, I'm going to ask you to take a look at an AP problem of how they would ask you to do this and work it out with me. Here's an AP problem. Consider the differential equation dy dx equals 1 plus y over x, where x cannot be 0 because of course it would be undefined. On the axis provided, sketch a slope field for the given differential equation at the 8 points indicated. Notice that there's really only 8 points that you're going to have to do this for. And that's really nice because the AP test doesn't have you do 100 of these. They figure if you can do these 8, then you're good to go. Alrighty, so let's use a little bit different color. So here we're going to go ahead and pick some values. We can't pick x equals 0, so maybe we should pick x equals 1. You're going to notice I put a y here. And the reason I included y in my table is because y now plays a role in what sine is, in what the slope is going to be. So both y and x play a role, so I'm going to put both of them. And I probably shouldn't have put an x. What I really meant to put was a 1. So x1, y0. I'm going to plug those into my differential equation, and you're going to notice that I get an answer of 1, which means my slope is equal to 1 at the point 1, 0. So again, I'm going to direct it in the direction of rise 1, run 1, or down 1, left 1. Same thing. And I get my slope. Okay? Let's go with the point 2, 0. And this time we're going to get 1/2 by plugging it into our differential equation. So again, I'm going to go up 1, but think of going over 2, or down 1, left 2. So I'm going to point this line in the direction of 0, -1. And I think what's important here is for you to realize that although it's subtle, this slope is less steep than the previous one because it's only 1/2 compared to 1. We're going to continue doing that for the remainder of the points. Again, I'm going to ask you to pause the video, finish the points, and then compare your work with mine. Okay, so here's the result of my table of values, and then here is the differential equation. You'll notice again that we have 0 slopes, positive, negative, but you have a steeper slope where you have a slope of 2 compared to a slope of 1 compared to a slope of 1/2, and over here are the corresponding negative slopes. This is only the first part of the AP question. There is more to it, but at this point this is where we're at, and I wanted to provide you with an example of what you'll be asked to do on the AP test. Pretty doable, pretty doable. The next skill that you need to gain today is being able to trace solutions on the slope field. Now we've kind of already done that when we trace the solution for cosine of x. But in this case, again, the differential equation is not too tough. You can see that it's 2x. You take the antiderivative, the answer will be pretty obvious. But one of the things that will happen on the AP test is sometimes they're going to pick a point, and you'll notice this one doesn't do it, but I'll do it right now. They'll put a point and they'll say, hey, draw the solution or Yeah, draw the solution to the differential equation using the slope field that contains the given point. Well, what that means is instead of just randomly drawing the one you want, they actually want you to go through the given point. Sometimes they call this point the initial condition. So what happens is you really just have to kind of follow along and make sure you hit that point. The slopes guide you. See how we have a 0 here, but then it starts to go up? And surprise, this is x squared, which is the solution to the differential equation. Actually, it's x squared minus some constant. We're not quite sure because they didn't label the y-axis. We're not sure that these are 1, 2, 3, and 4. This could very well be a different scale. But if you continue, this would be it if you have to hit that initial condition. But if they don't give you initial condition, you can just keep tracing all day long. And again, create that family of functions concept that we talked about earlier. Okay? So why don't you press pause, give it a try, draw a few more, and then compare it with mine. Okay, so you can see here I drew several more samples just to give you an idea of what that might look like. Let's go on to the next example. I actually have 6 of these. So in this one, you can tell that we have a negative slope here that levels off to a 0 slope and then increases again. Whoops. Let's try that one more time. Something like that. You can try a few more. Notice that it's not a connect the dots, so I'm not hitting every single point. I'm just sort of following the direction that the slopes tell me to go. Increasing, 0, decreasing. Increasing, 0, decreasing. Alright, and you can fill it in a little bit more. Go ahead and press pause, try it, and we'll go ahead and move to the next one. Here's a different one. It starts off with a negative slope, kind of following it along. As you can tell, it levels off here at 0, and now it's increasing again, something like that. And you can tell, whoa, sorry. You can tell that depending on where you start, it might level off a little differently. Let me see if I can get that to come down and then start to come up. Again, it's not a connect the dots. Just kind of follow the directions. Sometimes you don't even hit them all. Whoops, it's still a 0, and then it starts to move up. Okay, so there it is. You can go ahead and press pause and draw a few more just to practice. This one, of course, starts with a positive slope, sort of levels off, then you go positive. Again, positive slope, level off, continue positive, go below, positive, and you can start to see what that will look like. Again, you can go ahead and press pause and try a few more just to get an idea. This one really behaves differently depending on where you're at. If you are above the x-axis, it sort of seems to be increasing, but levels off at the end. So maybe something like this. Whoa. Okay. But below the x-axis, you can see how these are coming from 0 and going down. So it's not something symmetrical, and that's okay. It doesn't have to be an exact copy of the function below the x-axis. So you can see that. Alright, just depends. Again, if you're given an initial condition, all you have to do is draw one that goes through that particular point. I'll let you try a few more. The last example is an interesting one because it relates to the Earth's magnetic field. You can see how it sort of turns around here and comes back. Okay. And maybe creating a little bit bigger circular pattern. Okay. I'll go ahead and let you press pause, continue drawing them, and compare with me. Okay, you can see mine now and compare. I went ahead and Googled just out of curiosity what the actual magnetic field of the Earth is, and you can see these shapes here. Looks pretty close to what we're working with, so that's pretty neat. Last skill that we have to learn is matching slope fields. This is actually out of your calc textbook, page 325. If you want to pull that out, you can. It says use slope analysis to match each of the following differential equations with one of the slope fields A through D. Do not use a graphing calculator. There is a program that does this for you. It generates the slope fields. I'd have to give it to you. But of course on the AP test, whenever that program would give you an advantage, you're not allowed to use a calculator. So in the end, it's really just a demonstration tool. You have to be able to do these by hand. So our goal is to sort of find which of these slope fields belongs to number 1, 2, 3, and 4. And you got to really look for patterns. So in this first one of the things you're looking at is the fact that the slope of the differential equation is going to equal 0 when x and y are equal. Well, x and y are going to be equal at points like 1, 1, 2, 2, 3, 3, -1, -1. So it's kind of in this diagonal that you should start to see a 0 slope. I don't really notice that in letter A. I see positives, a 0 here maybe at the origin, but not enough to say that the pattern exists. If I go to letter B, you're going to notice I have a 0 slope here, here, here. This is kind of tilted, but you can still see that there's going to be a 0 slope, especially between those two. See how it goes from negative to positive? So there's definitely a 0 slope in there. And you can see that when the x and y value are equal, you get sort of like a ladder situation where the slopes are 0. You don't find that anywhere else. So we're sure that number 1 has to be B for sure. If you go to number 2, you're looking for x times y. Well, again, if x is 0 or y is 0, the slope is going to be 0. So you're looking at not necessarily when x and y are equal, but when x is 0 or y is 0, which is on the x-axis and the y-axis. If you look at the y-axis of letter A, it is 0. So that means x is 0 here, and it produces a 0 slope. So that's promising, except for if you look at the x-axis, when y is 0, those slopes don't look like 0 at all. They actually look like undefined. So I don't think that quite matches number 2. If we go to letter C, none of the slopes on the y-axis look like zeros. If you look carefully, they're all undefined. That definitely doesn't meet. And here we have 0. Okay, so here we have, let's see, x times y, 0. So you have a 0 here, here, here. So again, it's looking pretty promising because wherever x is 0, the function is 0. Now here, it looks like it's becoming 0. You can't quite tell that it is, but if you notice, both from below and above, you get this flattening of the slope, so you can kind of tell that they're going to be a 0. And if you need further proof, look at the signs of the slopes. In quadrant 1, both x and y are positive, so the slope should be positive, which happens in letter D. In quadrant 2, the slope should be negative because x is negative. Quadrant 3, they should be positive because both x and y are negative. which happens here. They're positive slopes. And in quadrant 4, the slope should be negative because y value is negative in that quadrant. Letter C does follow that same pattern, positive, negative, but again, those slopes in the middle don't match, on the y-axis don't match. So definitely number 2 will be letter D. Okay. All right, dy dx equal to x over y. Well, this is going to equal 0 when x is 0, but undefined when y is 0. So let's go back and look at letter A. Remember we had a bunch of 0 slopes when x was 0. So that's looking good. And we needed to have an undefined slope when y is 0. Well, that looks undefined to me. So I think we have a match. You see? Okay. Therefore, number 3 is going to be letter A. And the very last one that we need to match is number 4. Now, process of elimination, of course, says that 4 will be C. But let's verify. 4 will have to be 0 when y is 0, but undefined when x is 0. So when y is 0, let's go with x is 0 first. You see all these undefined slopes when x is 0? So that's telling me that so far so good. And when y is 0, you see all these leveled out? You can tell that it's going to be 0 on the x-axis, which is when y is 0. Okay? You can also know that, positive and negative signs. If they're both positive, like in quadrant 1, the slopes will be positive. Both negative in quadrant 3, also positive. And quadrant 2 and quadrant 4 will be negative slopes as a result of only one of the variables being negative. So number 4 is letter C. And that's how you match